Hey, what's up guys? I'm back with another LeetCode question. Today we're going to be doing problem number 1569, the number of ways to reorder an array to get the same binary search tree. So we're given an array nums that represents a permutation of integers from 1 to n, okay? We are going to construct a binary search tree by inserting the elements of nums in order into an initially empty binary search tree. Okay, so we have an empty binary search tree, and we're going to take those nums and we're going to keep inserting them, okay? Find the number of different ways to reorder nums so that the constructed binary search tree is identical to that formed from the original array nums, okay? So for example, given nums equals 2, 1, 3, we will have 2 as a root, 1 as a left child, and 3 as a right child. The array 2, 3, 1 also yields the same BST, but 3, 2, 1 yields a different BST. Okay, that makes sense. Because if we were to do, let's say we did 2, 3, 1, it'd be 2, then 3 on the right, and 1 on the left. And then, but if we did 3, 2, 1, then 3 would be at the root, which is already wrong. We can't have 3 at the root. Return the number of ways to reorder nums such that the BST form is identical to the original BST formed from nums. Since the answer may be very large, return a modulo 10 to the 9th plus 7. Okay, so we just did example 1 that was in the question, but let's look at example 2. So we have this binary search tree. We have 3 as the root, 1 as the left child, and then 2 of that right child. 2 as the right child of 1, and then 4 as the right child of 3, and then 5 as the right child of 4. And we have 5 other different possible ways to make that same binary search tree, and we have 6 total ways, including the first one, right? So the way you want to approach this problem is, okay, let's just kind of think about it intuitively, right? Hey, what's up guys? Fair disclaimer right here, another one. I kind of rambled on for the first 8-9 minutes, but I think it was really important because I wanted to kind of explain why the order matters in inserts, right? You have to really understand and see how the binary search tree works with inserts and how it's built up. So why does the order of the inserts matter? Why does one number have to be before the other number? And what's really happening when you flip the numbers around, right? So that's really important, understanding how inserts affect the buildup of a binary search tree. So that's why the first 8 or 9 minutes is pretty long. But once you understand that and kind of grasp it fundamentally and intuitively, then the rest of the answer just is really easy after that. We have this array of nums. We have 3, 4, 5, 1, 2, right? And now we want to, we're going to be taking elements from that array one by one, and we're going to be inserting them into a binary search tree, right? So when we insert them, when it's initially empty, we put in 3 first. So we just have 3, right? And then we go into, let's say we put in 4, right? So we have 4 on the left. Why did I do that? We have 4 on the left, and then we put 4 on, we put 4 on the right, right? Because 4 is greater than it, so we'll put 4 on the right. Then we're going to put in 5, and then 5 will come down here. I don't want to type it all out. Then 5 will come over here. We check with 3. 5 is greater than 3. We'll put it over here. We already have a 4, so we'll put 5 instead. We'll do the same thing for 1. We put in 3. Is 1 greater or less than 3? Well, it's less than, so we'll put it to the left. Okay, is it null? Yeah, nothing was to the left of 3 currently, so we'll just put it to the left. And then we put in 2. So we put in 3, or 2 is less than 3. Is 2 less than 1? No, it's greater than 1, so we put it to the right of 1. And that's how we'll build our binary search tree. Okay. Now, what's really important here, okay? Let's say we started with not 3 in the beginning. Let's say we started with 4 in the beginning. If we started with 4 in the beginning, then the 4 would be our root. So that's already out of the way. We always need to start with the first number as the root, right? Always start with first number as root. That always needs to be root. So you see all of these, 3 is the root, okay? Now, what can we add next? Well, we can either add the 4, the 5, the 1, the 2, right? But those are our possible next steps to add, right? Possible next elements to add. But what are our limitations? Well, we need to make sure the same binary search tree is formed by the end of all the processing, right? So let's say we added 4 first. Well, if we added 4, we have an initially empty tree. We added 4. Well, 3 goes into, well, put in, 3 is already in its right place. Then we add 4, and we see 4 is greater than 3. Then we'll put in 4 over here, right? And we saw that 4 went to its right place, right? We're trying to build this tree again. So 4 goes to its right place. Now let's say we wanted to add 2. Okay, let's just say we wanted to add 2 instead. So far we're trying this out. We're trying 3, 4. Let's say we wanted to add 2. So if I go in here, I see 2 is less than 3. So I have to go to the left, and I'll have to put in 2 right there, right? Right away we see we made a mistake. Okay? Because 2 is not in its right place. It's to the left of 3, right? It's automatically to the left of 3. It's the left child of 3. And we know 1 needs to be the left child of 3. So that's wrong. So what do we know now, right? We know that 1 needs to be picked next, right? Before we can pick the 2, we need to pick the 1. Before we pick the 2, we have to pick the 1, right? Because if we pick the 2, then the 1 would end up going over here, right? Then if we were putting in 1, let's say 1 is less than 3, so go to the left. 1 is also less than 2, then it go to the left. So we put in 1 like right there, right? And that would be wrong. Because the 2 is not in its right place, the 1 is not in the right place, it's already wrong. So we know now that the 1 needs to come before the 2, right? And why does the 1 need to come before the 2? Well, because the 1 is smaller than 2. The 1 is smaller than the 2, and the 1 is at a higher, or you could say a lower. Yeah, you could just say that the 1 is at a lower depth than the 2. So we have to add them row by row. That's the observation I'm trying to get at. The inserts need to happen row by row. So all the 3s need to happen first. All the elements at row 0 need to happen first with just the 3. Then the elements at row 1, at depth 1. Then the elements at depth 2. Right? So we could add the 3, and then we can add the 1 or the 4. It doesn't matter which one we add next. All that matters is either 1 or the 4 need to be added next. And then we can add all the elements to the next level, right? We can add the 2 or the 5. Well, what I'm trying to say here is what you notice when you're doing the inserts, you're building them level by level, right? That's the main thing you need to understand. So once you understand that a search tree is built level by level, then it makes more sense, because you can't insert the 2 in between levels, right? Once a level is built, right, for that path, then you can't put something in between it, right? It's not like I can take this 2, let's say we had this tree 3, then I put 2 to the left of this, and then I have to put in 1. It's not like I can push 1 in between 3 and 2 and kind of just squeeze it in there, right? I can't do that. I can't do that, right? So I need to make sure that everything greater than 2 happens first, so the 1 needs to happen first. Everything above the level of 2 needs to happen first, so 1 needs to happen first. And same thing with the 5 and the 4. So the 4 always needs to happen before the 4 or the 5, because the 4 is at a lower depth, or it's higher in the levels, however you want to think of it, than the 5, right? So the 4 is at a lower depth than the 5, and so the 4's level in that path is built first. So it's a little weird way of thinking about it, but once you start thinking like that the levels need to be built first before the next level can be built, then you're fine. Okay? So now what are we getting at? So from there you can kind of develop an answer. So we know that this level needs to be full first, and then this level, and then this level. And so now we know that the ordering, that's the only ordering that matters, that the levels need to be built first. So all the levels over here need to be built before all the levels here, and all the levels here need to be built before all the levels here. Is that entirely true? No, it's not entirely true. What I mean is all the levels in a path need to be built in that certain order. So the 3 needs to come before the 1, and the 1 needs to come before the 2, right? I don't need to fill up this entire level before I fill up this entire level, right? And I don't need to fill up this entire level before I can start filling up this level, Okay, I guess you need to fill up this entire level to fill up this entire level, but I can start filling up the 2 before I even add the 4 is what I'm trying to say, right? Because at the level of this level right here, this depth of 1, we have 1 and 4. But I don't need to fill up 1 and 4 completely. I can just put in the 1, and then I can put the 2. So what I'm really trying to get at is these paths that the tree comes down at need to be built in order. They have to maintain their order. But between them, between their siblings, they can be at any order. It has no effect. So the 3 needs to come first, and then the 1 needs to come before the 2. But we could either add the 1 and then the 4, or we could add the 4 and then the 1, or we could add the 1, then the 2, then the 4, or the 1, then the 4, then the 2. It doesn't matter. As long as this 1 is before this 2, as long as this 4 is before this 5, as long as this 3 is before this 4, and this 4 is before this 5. That's the only order that matters, right? So that's what you need to kind of pick up on, because that's how the binary tree is built with those inserts, right? Inserts are dependent on what's at the previous level, right? So once you kind of understand that, then the answer just logically follows. Now that we understand that, let's just review one more time. So the 1 has to come after the 3, and the 2 has to come after the 1, and it also has to come after the 3, right? Just by the transitive property. If 2 has to come after the 1, and 1 has to come after the 3, that means 2 has to come after the 3. Same thing with the 4 and the 5. The 4 has to come after the 3, and the 5 has to come after the 4, and that means it also has to come after the 3. So everything on the right side has to come after the 3, and everything on the left side has to come after 3 as well. But for the left side, right, the left side has to maintain its ordering within itself, right? Meaning the 2 has to come after the 1. Doesn't matter if the 2 comes before the 4 or after the 4, or whether the 2 comes before the 5 or after the 5. No, it doesn't matter, right? It only matters the 2 comes before the comes after the 3. That's all that matters. And the 1 comes after the 3. Sorry about that notification. And same thing with the 4 has to come after the 3, and the 5 has to come after the 3. It doesn't matter, and the 5 has to come after the 4. It doesn't matter whether the 4 is before the 1 or after the 1, or whether the 5 is before the 2 or after the 2. So what we notice here is that the ordering matters within their groups. Within the left group, right? Within the left, all the left children of the roots, the ordering matters within that group. And within all the right children of the roots, the ordering matters within that group, right? But relative to each other, this group and the left group and the right group, they don't matter, right? The left group and the right group can be ordered in any way. We got the 4 come, and then the 2, and then the 1, or the 4 or the 1 and then the 4. It doesn't matter. So the 1 can come first, or the 4 can come first. It has no effect. So that means what we can do now is, let's say we know the number of combinations, or the number of ways, whatever. I want to say combination, but the number of ways the left subtree can be built. The inserts can happen, right? The left inserts can happen on the left side. Or we know the number of, one second, let me mute that. And we know the number of ways that the inserts can happen on the right side, right? So we know the left count, the count of the ways on the left side, and we know the count of the ways on the right side. So now all that matters is how many different ways can we intertwine them, right? How many different ways can we intertwine them? Meaning, what I mean by that is, let's say this. We have 1 and 2 on the left side, right? And then we have 4 and 5 on the right side. How many different combinations can we mix 1 and 2 and 4 and 5? Right, and this is where math comes into play. If you notice, this is a basic combinatrix math problem. And just a disclaimer, if you don't know how combinations work and permutations and Pascal's triangle and how Pascal's triangle, you can deduce combinations from that, then I highly suggest, before you get into this, learn about Pascal's triangle, learn about combinations, learn about what n choose k means, and then come back to this problem, because it won't really help unless you know that beforehand. Where we have 4 different options. We have 4 spaces, 1, 2, 3, 4, right? And we need to put 2 in any of those spaces. This 2, right? needs to go in any of those spaces. So we can either put 1 over here and then 2 over here, right? Something like that. Or we could do 1 and 2, or we could do 1 and 2, something like that, right? So how many different ways can we fit 2 into a space of 4? How many combinations of size 2 can we have into 4 spaces? That's a basic n choose k problem, right? N choose k. Basically, we have 4 slots, and we need to choose 2 of them. That's all it is, right? So, and because basically when we fill in 2, then we basically have the other 2 filled out already, right? So it's n4 2, right? And let's just say it was, hypothetically, this was of size 3, this was of size 2, then we would choose 5, choose 3, right? Or we could do 5, choose 2, same thing. Because if we choose 2, then there's 3 left, and if we choose 3, then there's 2 left, right? So that's what you kind of need to figure out next, that it's a combinatrix problem, and we need to figure out how to do n choose k. Okay, and so once we choose n choose k, then we could just do n choose k, right? We either the left group, left count, or right count, right? Let's just say right count, and then we do that multiplied by what? The number of ways we could do the left, so num ways left, and then multiply by what? The num ways of right. Because now within the left group, we can get a different ordering, right? We can get a whole number of different ways we can order the left side, and same thing with the right side. Because within their respective groups, there's different number of ways, right? And within relative to each other, we also need to find the different number of ways we can fit them in. So we could do n choose right. How many ways can we fit them together? Then we just multiply by the left, the answer for the left, and then the answer for the right, right? Because for each left one, we could insert a right. So I hope that kind of made sense. I know this wasn't the best explanation, but I really don't want to redo this because I have like 3 more to do today. So it's basically n choose right, and I gotta turn my notifications off, times the number of ways left times the number of ways right. And so now we can go into the code. So once we kind of understand that, then the code becomes a lot more easier. So what we're going to do is we're going to split the left group and the right group. And the left is basically everything smaller than the roots. And the right is basically everything greater than the roots. And then we do n choose k, n choose left or n choose right. And we'll figure out how to do the combinatrix using Java. Because in other languages, they have utility functions that will calculate that for you. We're basically going to be using a Pascal's triangle. And if you don't know how Pascal's triangle helps you figure out combinatrix, then I suggest watching a YouTube video. I'll probably link it somewhere to figure out how that works. And so we can, from the Pascal's triangle, we can find out the combinations really simply, really quickly. And then we just recursively find the number of ways left and find the number of ways to the right. And there's base cases, and we'll kind of go over that in the code. I'll do that. Should I cut this? I'll just keep going. So how it's going to go is like this. So there's a little trick here where you use a static function to calculate and static variable to calculate the Pascal's triangle, so it doesn't calculate it on every call. So basically, if it's null, if we haven't calculated the Pascal's triangle, then we need to build Pascal's triangle, and that's down here. Very simply, our n is 1,000 because over here we listed the max is 1,000. We set it to two-dimensional matrix. Is basically a triangle, right? The first one is size 0. I mean 1, and then 2, and then not 2, 1 and then 3. Sorry, 1, 2, then 5. 1, 2. Whoa. 1, 2. Sorry, it is 1, 2, 3. My bad. Then we just fill in the beginning and the end with 1s. You kind of have to watch how Pascal's triangle works, where the beginning and the end are always 1s. And then we just slowly start filling them up. Calculate each one based on the previous one, right? The one to the left above and the one to the right above. And then we have to mod it. We have to mod it at each calculation, right? Because the number will get too big. We have modded by our mod value, which is 1,000,007, which they gave us. Not million. Whatever, it's 1,000,007. And then we build up the Pascal's triangle. So what I did was I only built it up once on the first problem, and it's a static variable, so you can reuse it. Then I convert everything to the array list. Then you just have to call it again with the list. And basically, if the size is less than 2, you return 1, right? Because if the binary search tree is of size either 1, then there's only one way, right? And so size 2, which is either the root and the left child or the root and the right child. It's only one way again. Then you get the roots. Then we're calculating our left and right groups over here, right? If anything is less than the root, we add it to the left. If anything is greater than the root, we add it to the right. And then once again, we've used a combinatrix right here. This I kind of is going to take too long to kind of explain how the Pascal's triangle works. But basically, this is our n, left dot size plus right dot size, right? This will be like 5 in this case, right? And then the left dot size, we could also do right dot size. It's going to be the same thing. Either 5 choose 2 or 5 choose 3. Doesn't matter. And then we mod it. We have to keep modding at every step. I think you can remove the first one, but it's fine. We just want to keep modding at every step because we want to make sure we don't go over. Then we multiply it, like we said, by the number of ways left, and then we multiply it by the number of ways right, and then that will just give you the final answer. Submit that just to show you guys. 33 milliseconds. Let's show you right here that you can also do the right dot size. I haven't tried this out, so I'm just hoping that I'm correct in this. I see right dot size. That's the basic answer. Please don't forget to like, subscribe, comment. Let me know if the solution helped you or didn't help you.